We are Noumena, and basically I'm Salvador Calva. I'm an architect, designer, and also developer here at Noumena. And also we're gonna talk together with Esther Vera, who is an electronic engineer, and we're gonna talk about evidence-based design and planning, predicting effects of design and planning interventions. Basically, we're gonna talk about urban mapping and sensing public spaces. Here's a little bit the content of what we're gonna tackle. Basically, sensing public spaces. What is Noumena? Also, what is the methodology? And we're gonna talk about the urban mapping use case. And then we're gonna jump to what is machine learning and computer vision applied to urban spaces, and also go a little bit in depth about what is machine learning and also computer vision. So Noumena it's founded since 2011, has been developed practice integrating cutting-edge technologies to study and analyze spatial dynamics, founded by Aldo Solazzo, Efilena Baceta, and Chirag Rangolia. Noumena's mission is to develop metrics and instruments to empower decision makers towards more efficient, resilient, and sustainable spatial solutions, and has been involved in multiple initiatives operating in build and environmental scale to define design protocols driven by data and machine learning. So here's the workflow. We basically collect data, then process data, and then make a monitoring of the spatial. Finally, for data collection, we use autonomous systems to capture reality. In Noumena, we digitize the physical environment, introducing devices as tools for spatial observation. We implement autonomous systems to collect data, detecting and monitoring the physical characteristics of a site through cameras and onboard sensors. Our goal is to integrate optical data to establish criteria for spatial decision making. Then for data processing, with digitized physical environments, we are experts in reconstruction built environments to convert physical components into data. We are adopting state-of-the-art technologies to digitally reconstruct faithfully spatial representations. Noumena develops digital twins and to optimize the maintenance operations of physical assets, systems, and manufacturing process. In spatial monitoring, we use AI-driven spatial analytics. We develop spatial algorithms to reveal invisible patterns of a human behavior and spatial expression. Through computer vision and machine learning, Noumena implements strategies to track and monitor spatial dynamics, uncovering associations between each individual component. Our aim is to produce informative geographical representations of spatial occupancy to drive strategies such as energy consumption, urban analytics, farming practices, or management for on-site construction. Then this is the three branches that we have, for example, or we're working with. We are, as we mentioned before, we talk about urban analytics, precision agriculture, and also commercial spaces. In urban analytics, we use image analytics to build better cities. We implement machine learning and computer vision to provide accurate estimations of actual spatial dynamics occurring in the public scene. The integration of vision-based technologies allow us to inform data-driven decisions and the applications of urban solutions for traffic and mobility surveillance, classifications of urban components, land use classification, analysis of environmental conditions, and infrastructure monitoring. In farming, is basically precision agriculture. Leads the integration of vision-based applications in farming sector, introducing autonomous systems to facilitate the integration of technology for food. The services provided targets mainly are crops monitoring, spot spraying pesticide, yield management, weeding, and AI farming tools. For commercial spaces, data-driven business growth, integrating, so we develop and integrate software and hardware solutions to capture, analyze, and process stored data. Our infrastructure includes sensing devices to collect information from the physical space, then for artificial intelligence, algorithms to process data, and we develop online platforms to access and visualize and monitor the results. Basically, all this information we use for customer analysis, product placement, product interaction, store layouts, and target campaigns. Then now for urban mapping, we develop a project which is called Sensing Public Space. Basically, Sensing Public Space developed for qualitative urban studies. This is a little bit more theory or introduction for how we can, or the history of sensing public spaces. And what we do is basically to tackle with quantitative and qualitative. Now for qualitative urban spaces, cities serve as the backdrop for majority of our days, shaping our visual environment, the immaterial background of our lives. What insights can we gain when we delve into a visual aspects of the cities that go beyond more architectural style and urban design? Is the visual representation of the city's comprehensive reflection of the concealed social and spatial dynamics and principles at play? This line of investigation gained significant traction in the latter half of the 20th century as prominent urban scholars observe and respond to swiftly transforming urban environments. Subversive approaches and ever-going investigation of urban. This line of investigation gained significant traction in the latter half of the 20th century as prominent urban scholars serve to and respond to swiftly transforming environments the work of Guy Debord, an international situationist, brought an innovative methodology to approach the complexity of a urban threat first-person perspective, seeing the effective of traditional urban planning and consumer culture towards the homogenization of urban landscape. The approach of the derived drift mostly consists in aimlessly wandering through the city, allowing oneself to be guided by the landscape and one's own intuition rather than the predetermined route of destination. The image of the city, the pioneering work of Kevin Lynch. As I mentioned before, this is going to be a little bit theoretical, but then we're going to jump a little bit more technical. So if you have kind of question or kind of, I don't know, like highlight of want to comment, please let me know. But for now, the pioneering of, I'm going to talk a little bit the theory about this, but then if I don't want that you go to sleep or something like this, so you want to interact or mention something, let's go. But then, so bringing forward concepts such as psychogeography, strategies like the one of the board inspired many scholars in the following years. It is, however, since Kevin Lynch pioneered work in the image of the city in 1960, that urban scholars have increasingly turned to a visual and sensory methods for studying the complex life of the cities in a more scientific manner. There, it explored how people perceive and navigate urban environments through mental maps by analyzing key urban elements, paths, edges, districts, nodes, and landmarks. Although offering valuable insight into urban navigation and design, this approach faced criticism for prioritizing physical aspects of the cityscape at the expense of the underlying social dynamics. People first, cities and communities. On the contrary, Jane Jacobs favored the messy vitality of the street and its complex intermingled of the users and users as the key elements to address the representation of and usage of public space. She expanded sensory approaches, death and life of great American cities in 1961, advocating first-hand observations of communities and neighborhoods as key resources for urban studies. Multiple dimensions towards the right to the city. In the productions of Space in 1974, Henry Lefebvre presents through provoking perspective on the nature of space. He presents the space as dynamic, socially constructed entity, as opposed to a passive container. To address through the category of conceive and perceive and live, cities become multidimensional experimental places, highlighting the role of power structures in shaping space, particularly through urban planning and design. He called more holistic understanding to, to the urban, considering not only the physical aspects of space, but also its social and cultural dimensions as well, and as its governing forces. Sensing public space, quantitative urban studies. In parallel, more quantitative approaches were emerging, opening the door to groundbreaking technologies and the city's scale disaster. Urbanists like William H. White and Jan Gehl played a pivotal roles in this shift by incorporating innovating technology, particularly video cameras. They revolutionized and the way they to revolutionize the way we analyze and comprehend urban environments, paving the way to empirical urban studies. Building urban data sets, the birth of data gathering. In his most influential, in sorry, in his most influential 1980 book, The Social Life of Small Urban Spaces, William H. White established the basis for empirical urban research by emphasizing meticulous first-hand observations and underlying the significance of data collection in comprehending and efficiently managing of urban environments. This is about White, 1980. While White's approach offered an effective and replicated method of analyzing urban space interaction, it demanded extensive time spent in public urban spaces, painstaking recordings and annotation, and soon become impractical to large-scale studies. The smart cities promise, unlocking cities through data. Over time, the rise of data science and advances in computing technology place a growing emphasis on data in various fields, including urban studies. This shift gave rise to concepts like smart cities, driven by the potential of data to optimize complex urban environments and attract economic interest in city planning. Around the turn of the 21st century, cities worldwide began adopting IoT technologies, utilizing sensors for air quality and traffic monitoring, and CCTV cameras for security, transforming into city-scale information systems. The smart cities promise, unlocking cities through data. Around the turn of 21st century, cities worldwide began, as I mentioned before, the IoT, and also the CCTV cameras. But now I'm going to jump for, while proven insufficient and inherently leading to inconclusive understanding of urban life due to the heavy reliance of corporate interest and issues of data ethics and privacy. These experiments offer fertile ground for data analytics to thrive. Then we jump for computer vision models. This is a little bit more like the core what we do in Noumena as well. So harnessing the computational eye. Among other data streams, the extensive data collected from CCTV cameras and sensors deployed worldwide has significantly contributed to the development of modern computer vision models. Capturing diverse real-world scenarios, these datasets provided the foundational material necessary for training advanced algorithms. By analyzing this wealth of visual information, computer vision researchers were able to refine their models, enhancing their accuracy and robustness. The diverse array of data points enabled the algorithms to recognize and process various objects and scenes in real time, making YOLO like it's another computer vision model that you only live once. It's more a little bit the background of if you heard before this YOLO word before, but you can familiarize a little bit like for this, but now in this case is for a computer vision model or architecture, and similar models highly proficient in tasks such as object detection and enumeration. urban mapping in Barcelona. This is a little bit the map of Barcelona for the one that want to appreciate a little bit where the Sagrada Familia is and the superblocks and Diagonal. Another example for urban for map of Barcelona. But the case study is based on the superblock model. This is a towards citizen-centric cities. Barcelona Super Area project introduced in the mid 2010s aimed to transform urban neighborhoods by reminding the city blocks into pedestrian-friendly superblocks. Superblocks prioritize pedestrians and non-motorized transportation, reducing the traffic and improving the quality of life for residents by creating more sustainable and livable urban spaces. The superblock model. The first interaction of the Barcelona Superilla project in 2016 faced significant criticism from the press and the general public. The community of San Martí, in particular, expressed their discontent as they felt the superblock was imposed with force and criticized the top-down approach that exclude their input in the planning process. This criticism highlighted the challenge in implement urban transformation of this scale and underscore the importance of the community engagement and collaboration in such projects. This is some of the map of where the superblocks had been developed. And this is another map where we can see the place or where we place the cameras for the first iteration of our study. So we have 7 cameras. The camera sensor were RGB. We record 3 times: Monday, Thursday, and Sunday, the 24 hours. Then the streets were the Superliga, Consell Descent, and nearby Valencia. And the amount of data were 600 gigabytes. Also, this is some of the installation of the camera process. You can see in the left is the camera that we use. Some of the cameras we develop in Noumena, and also we have some use like CCTV cameras that some of them are already on the market. So basically, we are able to capture or collect information from these type of cameras as well. The data preprocessing, basically we reduce the frame rate, we correct the distortion with image calibration, and also we can create corridors. I'm gonna explain a little bit about this. Some of the issues that you can see, basically, this is the down below on the right. You can see that we have different colors that basically help us to capture better information of each class that we are interested. As you can see, the blue one are cars. So then the pink one is also only for pedestrians, and we capture only information from pedestrians right there. And then you can see the bicycle corridor that is only able to capture in that place, in that specific place, the bicycles for have a better and accurate counting system. This is like a demo for how it works. Of course, for privacy, we try to just basically censor or just cover all with cover all the objects just for terms of privacy. But then jumping for the algorithm itself, basically we use this model also, as we mentioned before, we use the Majolo model. In this case, it was the version 7. It's an open source developed by Ultralytics. It's a training Coco dataset. And the classes detected were pedestrians, cars, bicycle, motorbikes, small trucks. Also, we use another algorithm which calls Norfer. And also we custom some or refine some a little bit these algorithms by our own. This is and then this is the post processing. And basically, these are the type of dashboards and charts that we develop in the company for have a better understanding of what is happening in these places where we use the cameras. This is another data visualization. It's over the same day, but basically the different times and the same street as well. So this is the type or another type of visualization that we use for decision making as well. And finally, the ground of truth comparison. Basically, we also use different methodologies for better understanding how we can improve the models of what we need to fine tune. And basically, this is it. Thank you. Now I'm gonna give the word to Esther.
Hello, everybody. Thank you very much, Salva, for the first part of the presentation. My name is Esther, and I'm a computer vision engineer, and I'm working at Noumena, like Salva. And right now I'm going to start the part 2 of the presentation, that is machine learning and computer vision applied to urban spaces. So first of all, I would like to do a definition of machine learning. So machine learning is a tool for turning information into knowledge. So what basically does machine learning is like we have a group of data, a lot of data, and we want to understand all this data in an easy way and extract the information that we would like to know. So when we have large amounts of data, like gigabytes or terabytes, it's very difficult for a human to analyze all this data and get information from it. So what we do is creating these models that are able to imitate the way that humans learn, and we improve the models, improving the accuracy and the outcomes that they give us. So in the past 50 years, this has been possible because of two things. First, because we have an explosion of data thanks to computation, and also because of the computational power that we have now in our computers is much greater than before. So with these machine learning techniques, we are able to understand and get all this data and extract the patterns within this complex data that it will be very difficult for us as humans to understand and get information from. So with these outcomes, we're able to predict future events, and also this model help us in decision-making processes. So first of all, you have to understand that machine learning is inside the artificial intelligence term. So artificial intelligence encompasses machine learning and also deep learning. The AI includes not only these terms, but also the functions, mathematical equations, and other statistic methods. And then we have more like in-depth approaches like machine learning. That is when you use these models to train this data and get this information. And deep learning that includes the use of neural networks in the software. So you see that this has been something that has been developed since the 50s until now. So in the next slide, I would like to introduce a little bit of the history of machine learning. So the first time that this term appears is with McCulloch and Pitts. They are the people that did the first paper talking about the artificial neuron. So it's like defining mathematically how a neuron works, but in a mathematical way. So this was the beginning of the machine learning scope. Then we'll talk later a little bit about Alan Turing, that is considered as the father of computers, and then it's also worthly mentioning the work of Rosenblatt, that it was the first one of creating a neural network, a hardware-based neural network that was called the perceptron. Then, as you could see in this timeline, we have like 3 golden ages and we have 2 dark ages. So the first dark ages start with the short problem. What it means is that at the beginning, these first models, this perceptron that we talk about, they were only like linear models. So it was very difficult for them to approach to detect other things, to solve problems that were not linear. So when you could have two different kind of data, you could separate them by lines. But when you need a more difficult structure, we didn't have the power to do it. So this led to the first dark age where the investors and the people researching in machine learning started decreasing. After that, we started the second golden age where they were implementing new improvements to these neural networks that were starting, like they introduced the multi-layer neural networks, the backpropagation, and other methods, and they were able to solve more complex tasks. And then it started the second dark age due to the difficulty to train these models with the computers of that area. And then right now we are in the third golden age, where we are having all this revolution with neural networks that allow us to identify things with images, with large amounts of data, train very huge models, and like the last advancement that we had, like with ChatGPT and other kind of models. So, as I said in the next slide, I wanted to mention Alan Turing because he's the father of computers. So he was the first one defining what is thinking for a computer. So we will define thinking of the process by which we evaluate features learned from past experience in order to make decisions about new problems. So with this definition, we can say like machines cannot think. Like, okay, they get this data, they are trained, and they like they can extract these patterns, but they are only following rules. They are following mathematical methods, instructions, but they are not understanding what is happening inside the data. We are the ones that are giving them meaning, depending on what we want to achieve. So this leads us to some questions that will be like, will machines ever be able to think? Like, maybe yes, but not in a way that we do. And also, like, we have to separate like what it is thinking that from consciousness. Like they will be able maybe to think and how to interact with this data, but not to be self-conscious of what they are doing it and why they are doing it. And also we have the question like, what will happen if they could think? So that's we will leave that questions for the science fiction films that they already have so much to say about it, depending if they have like self-consciousness and other values or or things that they want to achieve, or they will cooperate or not with us. So Alan Turing also defined what we call the Turing test. It was like we are the interrogators and we are talking with two different people. We are talking to a machine and to a person, and we are getting the answers via a test. And we don't know if we are talking to a machine or to a person. So we have to guess if the answer is from a machine or from a person. So what Turing says is that if we are not able to distinguish between the answer is from a machine or from another person, then we could say that the machines are thinking. So next, like I said, like Frank Rosenblatt was the first one that did this machine. That was the first machine which it was capable of having an original idea. So this machine was able to recognize some visual patterns, but it was not working as expected. So it was some broken expectation that led us to the dark ages. In the next slide, we'll see like the nearest neighbor algorithm. That was the beginning of the basic pattern recognition. And this algorithm is useful for the solution of the traveling salesman's problem. That is basically that we have different cities and we want to understand the shortest path from one city to another city and not repeating the cities. So what we do is like we have this kind of graph representation, and with this nearest neighbor algorithm, we're able to solve this problem. So this was like the first approach we had, and it's something that is very used right now, like by a lot of people, by mailing companies, by Amazon. Much like this problem was the beginning, but now we have methods that are much more optimized for it, and depends on the traffic and the roads and other situations that we'll face. Next, please, Salva. So then, as I said, like after that, we have it was introduced the multi-layers, so that solved some of the problems that we had before with the neural networks. We introduced the backpropagation to have better models, and the boosting that was using these small and weak models that could be joined between them and have a stronger model. And then in the present, in the next slide, we see now in the present that we have a lot of different neural network models. We have the long short-term memory models that are very used for speech recognition. We have convolutional neural networks very used for facial detection, object detection. We have the GANs that we will talk now in other slides that are for image generation, and we have the transformers, for example, for ChatGPT. So for convolutional neural network, we have YOLO, that is one of the most used neural networks. As you see, it works pretty well in the urban spaces. It's able to detect in real time cars, traffic lights, people, trucks, buildings, vegetation. So it could be used for analyzing the urban space. Like you could go with a camera in the street and be able to detect everything that is happening around you. And also, like we did in the urban mapping project, we placed these cameras in the lighting of the streets, and we were able to analyze the path of the people walking and the cars and everything. So what it does, YOLO, is having this image. It divides the image into different regions and predicts bounding boxes and probabilities of the classes that it's able to detect. And next. So I wanted to show you also the generative adversarial networks because I think they're really interesting in this topic. So we have like two models in one. We have random noise, and with this random noise, we have a generator that will be the model, and the generator creates a fake image. So in this case, we want to create a fake building, as we have here the image of the generated image, and we have a discriminator, and the discriminator has to be able to distinguish between the generated images and the real images. So what is happening here is that we have a model that is the generator that wants to create the most accurate image for be able to pass through the discriminator. So if I generate an image and the discriminator says that this image is real, is that the generator is working well. But then the discriminator will say, okay, I got it wrong, so I have to train myself to be able to distinguish better which is what is real and what is generated. So this will be this kind of model, for example, is used for Midjourney and another software that is available online. So it's not only for buildings or for other images, like we use it, for example, for faces, to generate fake faces, and also to be able to distinguish if this video of someone talking, a famous person talking, is fake or is real. So in the next slide, you see this, for example, are building generated images by using these models. So the good thing about this kind of models is that you can like approach it in different styles. So what I mean is like you'll see an example in the next slide. Salva, you could, yes, perfect. So you see, for example, we have a map of the city. So the map is from Milan. So we have this image from Milan as satellite image. So we have in red the buildings of the image, we have in green the vegetation, and then the paths and the roads. So this is the real map, and then with this kind of neural networks, we are able to recreate this environment, but in a different style. So for example, we wanted to have like the same structure of the city, but with a Venice style, like Italian style. So we'll say, okay, we train this model and we get this generated map that we see is more like the roofs and the roads are more similar to this kind of style. Still, there's so much to improve in this image generated, but it could give us some ideas or some insights about what we can do with this kind of models. Also, like we have the sample of Los Angeles model, like it's much more gray and the roads are also like less vegetation, and the environment changes from one image to another. But we have that from the same input, we can have like different outputs. Okay. So not only can be used for this kind of information, but there's a lot of applications that can be used with machine learning, like analyzing sales data, for doing product recommendation, image recognition, sentiment analysis, healthcare efficiency, and much more. So also I wanted to mention that there are three types of machine learning. That is the supervised learning, is when we use labeled data to train a model. So we have in this case squares and triangles. And with the supervised learning, when we put this data we don't know, the model will be able to tell us if we are seeing at a triangle or at a square. Also, we have the semi-supervised learning that is very useful when we have large amounts of data that we are not able, or we don't have the resources to label. So we have some labeled data and some unlabeled data, and then the unlabeled data will be placed, depending on their characteristics, it will be placed with the labeled data in one group or another. And then the unsupervised learning, that instead of dividing the data between the classes, we are dividing the data between clusters. So they are grouped depending on their features. So I want to introduce now what is computer vision and how we use it right now. So computer vision is the field of AI that uses machine learning to teach systems to extract information from digital images or videos. So in this case, we have the sample of a tennis player, and we're able to extract from this video the human pose that he's doing, also the kind of movement with the racket that he's doing, and where he is placed in the image during all the frames. So these kind of algorithms analyze this visual content and depending on, and it gets information from the shapes, from the color and the motion, and extracts these features. And these features can be labeled and used for training machine learning models for recognizing objects or actions in other videos. So in the next slide, you see like for understanding computer vision, we also have to understand what is an image. So an image is built of pixels. We have a binary image that is when the pixels are 0 or 1. So the black pixels are black, and the pixels with a 1 is that they are white. So in the next step, we have the grayscale images. That is when instead of using just a 0 or a 1, we have pixel values from 0 to 255. So this is much more detailed. We can see the shadows much better. So we have the same, like in low values, we'll have dark pixels, and in high values, light pixels. And then we get to the RGB images. So we have the color images. Instead of having just one matrix, we have three matrices, and they are each one for each color. So we have one matrix for the reds, another for the greens, another for the blues. And when we add these three channels together, so when we have this image. So this information that we can extract also from the images, these different colors. And this, in the next slide, also, like we have these images can be represented in different color spaces. So the color space is basically for the organization of colors. So the most common is the RGB. That is the one that we use in our daily basis. But also we have the HSV that is very common for doing color detection in images. And we have other kind of color spaces depending we want to print in a newspaper, or we want to use Photoshop or digital applications. We use other kind of color spaces. So for using computer vision, a very common tool that is usually used is OpenCV. So OpenCV is a computer vision and machine learning library, and is worldwide used for a lot of companies, students, and maybe you already know it, and it's very used for common computer vision application. So with OpenCV, we can do image transformation, feature extraction, tracking, recognition, identification, classification, like everything you want to extract from an image, you can do it with OpenCV. It has more than 2,500 optimized algorithms, and millions and millions of downloads. There are also other tools, but this is the most common, I would say. So some examples of what you can do with this library is extracting the edges of an image, blending images, doing some filtering on the images, also detecting the depth in an image, and changing the colors of this image using the histograms. The next slide. Okay, some applications of computer vision, as we were saying, like facial recognition, surveillance, counting vehicles, people, detecting defects, navigation of driverless vehicles and robots, object recognition, medical image analysis. And for example, like in the video, I think you can click it, Salva, on the right. I think Salva is frozen.
Yeah, I
No.
think like it's
Okay.
it's just loading.
Perfect. So you see, for example, like from a 2D image with different cameras, we're able to detect like you can stop it there. So yes. So with with an image, we are able to detect the landmarks, the facial landmarks of a video, and we're able to do the 3D reconstruction of this scene. So this is done in a controlled environment, but here, like for example, we do this kind of 3D reconstruction in different spaces. In the next slide, you will see another example. This is part of a project I did for my final degree project. So this is from satellite images. And what I was trying to do was understanding the development of the cities during time. So I had these images, satellite images in different months during several years. So I was identifying each building with a number and trying to count how many buildings were there before, and identifying like the same building with the different years and how it was like in the same position and how it was appearing and like how was developing this space during the years. And next sample, like for example, you can do like cementation and getting the vegetation, cars and the road, and also for background extraction and getting how the people is movement in the environment. Another use case that I wanted to show you, this from an intern that is now working with us also in Noumena. So here we have also from satellite images, we have house detection, road detection, and path detection. And all this information, we are mixing it together and extracting like information about how the roads are integrated inside these images. So we join all this information, do some training a model. We train a model and we optimize it. And what we're doing is propose new paths for the users. So we're giving, with all this information, we're able to understand how the paths and the roads are integrating within the city and give the user new alternatives for how to walk in the city. And that will be all.